Welcome to my 2025 Geometric Optics Computational Physics Challenge video. I plot the refractive index of water and BK7 glass against visible light wavelengths using the Selmayr equation and the empirical formula provided. And then I map it to the RGB values using the visible color light function on Plotly. For task 2, I used the data provided and plugged it into the thin lens equation, which was rearranged into a linear form to allow me to get the y-intercept. I also assessed the uncertainty using ODR, and the results were a focal length of 15.11 plus or minus 0. To prove Fermat's principle and Snell's law, we have graphs where C1 and C2 are the wave speeds in the two media, and the curve will always have a medium. And according to Fermat's theorem, this is the path that the light will take, which means that the red dot is the minimum point. And in reflection mode, the minimum occurs at exactly x equals L over 2 when the setup is symmetric, which corresponds to equal angles of incidence and reflection. Whereas in refraction mode, the minimum occurs at x where Snell laws hold, as the right graph equals the ray path and the actual geometry of the light path from A to S to B, using the x value from the minimum time on the left graph. Task 5 is a plane mirror with a slider to set the mirror height in pixels, which show the reflected image and marks the mirror line. Task 6 to 7 is a thin lens with a slider for focal length and object distance. The buttons for preset real and virtual image conditions allow the image transformation and lens equation results. Task 8 is a concave mirror with a slider for radius of curvature and object distance. It shows the transformed image and focal length. Task 9 is very much the same as Task 8, but with a negative radius of curvature. Task 10 is an anamorphic image creator, with sliders set for a circle radius, radio scale factor, and sector angle, and a button to position the source circle at the base. The thin lens and mirror equations are applied to compute the image. For task 11 and modeling rainbows, I use the speed of light frequency conversion alongside the formula used in 1b for the dispersion model of water, Snell's law of entry refraction, ray deviation angles, and angular position, Fresnel reflection and transmission losses, as well as mapping the altitude and azimuth in space relative to the antisolar point to calculate the arc of the rainbows. For task 12, I coded a matplotlib model of a prism to display the interactive ray tracing diagram of a white light entering a triangular prism, which uses refraction and dispersion of light beams and changing the incident and apex angle to alter the light dispersion, which is also plotted in the graph. The code features 3 sections: white beam entry, dispersion inside the prism, and the exit phase.